Okay, I'm going to give you a list of every star, or at least every star that I could find. So, here we have main sequence stars, which are hydrogen burning, pretty simple. They get big and bright the more massive they are, and hotter, and yeah. And then we have giants, which any star after its main sequence phase with a mass more than 0.5 solar masses will probably become a giant at some point. Stars with more than 1 solar mass will sometimes become a supergiant, but usually only when it's more than like 2 to 5 solar masses. If it's more than 10 solar masses, it will spend most of its post-main sequence phase as a supergiant. These guys, they're hypergiants. They are hypergiant. They're big and bright, and sometimes really hot. These guys form when a star of more than 15 solar masses leaves the main sequence phase. Then we have other post-main sequence stars. So we have hyperluminous blue variables, which if you have a very massive star that's just arbitrarily bright, it may have an episode, maybe lasting a few years to decades, of it being more than 100 million solar luminosities. But this is ridiculously rare. Wolf-Rayet stars are just really massive stars that are very hot and losing a ton of mass. They can reach hundreds of thousands of degrees Kelvin and be millions upon millions of solar luminosities. Then we have subdwarfs, which are not to be confused with white dwarfs and red dwarfs and the like, which are basically just smaller, dimmer main sequence stars. They are still technically in the main sequence stars, but I put them on here. I don't know why. And then blue dwarfs are when a star between 0.08 and 0.5 solar masses leaves the main sequence phase. Basically, it's not blue, but more of like a whitish blue, and the star doesn't get all that much bigger, so it's not super bright. Then we have post-stellar objects. So there are two types of white dwarfs, which are the carbon, nitrogen, and oxygen white dwarfs, and the oxygen, neon, and magnesium white dwarfs. Oxygen, neon, magnesium white dwarfs are very rare because there's a narrow mass range that often leads to a supernova. Pulsars, basically, they're bright and spin really fast and have rotating jets, so they sort of pulse from Earth's perspective. Then we have magnetars, which just have very strong magnetic fields. Then we have non-pulsars, which are exceedingly rare, and pretty much every neutron star has a fast rotational period. And then stellar mass black holes are, you guessed it, stellar mass black holes. Their radius is the Schwarzschild radius, since they can't get any smaller due to time dilation. They're sometimes extraordinarily bright due to their accretion disks. And yeah, and then the next one we have collapsars, which are basically just fast-spinning stellar black holes with rotating jets that are often more massive and often a lot brighter. Okay, then we have exotic stars. Blitzars are neutron stars that if they slowed down their spin, they would collapse into black holes. Quark stars are stars composed of sort of neutrons and protons, except the lines between them get broken and blurred, so it's just a sea of quarks. Then electroweak stars are stars supported by electroweak interactions. Boson stars are stars composed of particles with an integer spin, so basically an integer multiple of the reduced Planck's constant in joule seconds. So then bosonic stars could be supported by radiation pressure or a self-repulsive action. Like, theoretically, a very, very dense massive object composed of W bosons could theoretically be a boson star, but it would decay in like 2 seconds and blow the f up. I mean, it would decay in way less than 2 seconds, but it would just blow up and destroy everything around it. Theoretically, you could have a photon star, basically if you trap a ton of photons in orbit around a black hole, and you have some sort of mechanism to stop them from sort of knocking each other into the black hole. But yeah, and then black dwarfs are just white dwarfs that have existed for a really long time and have cooled down a lot. Dark matter stars are entirely hypothetical since we have no clue what dark matter is. So there have been observed chunks of dark matter, but they're galactic scale and not like stellar scale. And dark matter interacts the same way as normal matter with gravity, so it's probably true that dark matter stars exist, but they're unlikely to be anything like what we think they are. Iron stars are basically, if you just wait enough time, just by chance, all of the nuclei will just bump into each other and form iron. It can't go past iron. I mean, it theoretically can, but it's not going to go that much further than iron. Then Thorne-Zhitkov objects could exist. We have multiple candidates for them. It's basically just a supergiant with a neutron star at its core. They can only exist for, like, less than a year or century. Even that's a stretch. So, like, very short in a stellar time scale, because then they'll just go supernova after, like, a year or two.